So good morning all. Now we will see Gauss law and different forms of Gauss law. So the Gauss law states that the total electric flux through any closed surface is equal to the total charge enclosed by that surface, where psi is equal to Q enclosed is equal to area integral d dot dA equal to volume integral rho v dV, where psi is a flux, Q is a charge, d is a flux density and rho v is a volume charge density. This form is also known as integral form of Gauss law. And one point that you have to keep in mind is here the area vector dA or differential vector dA is always perpendicular to your closed surface S, and flux density D is also perpendicular to your closed surface S. Now we will see some other forms of Gauss law. We know D equals epsilon 0 E. If you substitute that equation, we will get psi is equal to Q enclosed is equal to epsilon 0 integral E dot dA, which is equal to rho v dV, which is another form of Gauss law. Then also we can write del of D is equal to rho v, which is the differential form of Gauss law, or otherwise a Maxwell's first equation. Now this is a closed surface, and in that closed surface I have selected if I am selecting a small surface along this closed surface, then your area vector dA will be perpendicular to the surface, and the flux density and electric field will also be perpendicular to the surface. Next we will see different applications of Gauss law. This Gauss law is specifically used to find out the field of a closed surface. So the surface should be closed, then only you can apply Gauss law. First we will find the electric field for a point charge. Point charge means the size is very small. So first what I am going to do is, here is a point, this is your point charge, and what I am going to do is I am going to draw a symmetric spherical Gaussian surface surrounding the charge. So this is very important, that whenever you are asked to find out the electric field of a charge using Gauss law, first you have to draw an imaginary Gaussian surface which is symmetrical surrounding that particular charge. That means now the surface is closed, so that you can apply Gauss law. Okay. Now on that closed surface I am selecting a point P, and here is my charge. So what happens is, from this charge the electric field lines will move towards the point P. Okay. Now near to this point P I have drawn, you can see here, the electric field intensity and dA perpendicular to the closed surface. I already said that this dA and electric field intensity will be perpendicular to the closed surface. So here I have taken the point P. So with respect to that point P, I have drawn E and dA perpendicular to this. If I am taking this point here, then I can draw dA and E perpendicular to that point like this, like this and like this. Then since the Gaussian sphere we are drawing is symmetrical, the charge distribution will be uniform around this point. That is also very important to be kept in your mind. We are choosing a uniform or a symmetric sphere, hence in this small area the charge distribution will be uniform. Not only in this small area, throughout this outer surface the charge will be uniform. Now we are making analysis with respect to this small area. That's why I told that in this area the charge will be uniform, and hence the flux density and electric field will be a constant. So to evaluate the electric field of any charge, we have to assume a symmetric or uniform spherical Gaussian surface surrounding the charge. In a uniform surface, charge will be distributed uniformly, hence we take a small incremental area. Hence if we take a small incremental area or area vector dA, there d and t will be constant. Now I am going to write the Gauss law. Psi is equal to integral surface integral of E dot dA, and you know E dot dA is equal to E dA cos theta, which is equal to Q by epsilon. This is our Gauss law. And in this figure, now I have drawn a red line, a rectangular box here, this one. This shows that dA and D are perpendicular to the closed surface. Now we want to find out the angle between dA and E. Since both are perpendicular to the surface, the angle between dA and E will be 0. So dA and E are in the same direction, hence the angle between them, theta, will be equal to 0. So psi is equal to E dA cos 0, which is equal to E dA, which is equal to Q by epsilon 0. And also we know E is a constant since the surface is uniform. So I can write Q by epsilon 0 is equal to E integral dA. I have taken E outside. So since we are using a spherical Gaussian surface, you know integral of dA equal to 4 pi r square. I am substituting it. Q by epsilon is equal to E into 4 pi r square. From that I can find out E, that is equal to Q by epsilon 0 4 pi r square. This is your electric field intensity. Also we know D is equal to epsilon 0 E. If you substitute that equation, you will get the flux density equals Q by 4 pi r square into unit vector AR, because here the flux density is along the radius R. So this is the final expression for point charge. Next, we will find the electric field for line charge. So this one is my line charge I've drawn here, and you know since it is a line charge, the charges will be distributed at both the ends of this line charge. Okay. Now in this case I am using a cylindrical Gaussian surface, okay, which is uniform. So that is drawn in red dotted lines. Now it is a closed surface. So here the line charge is on the charges are on the left hand and right hand side of our line charge. So you know how the electric field will flow. Electric field will flow towards the right of the line charge and also towards the left of the line charge. So if I am taking a point P on my Gaussian surface, and if R is the distance of this point P from my line charge, then I can draw electric field in this direction, right? Because here the electric field is flowing in this direction. Okay. Now if the electric field is flowing in this direction, then it is understood that the flux density D also will be in this direction, and this is a closed surface, and dA will also be perpendicular to the closed surface. Okay. We are drawing perpendicular line. This is how the line appears with respect to the curved surface of the cylinder. Okay. So now electric field and dA both are perpendicular to the closed surface. Now you have to imagine that you are having a cylindrical surface which is placed upside down, and the charges are flowing on right of the line charge and also towards the left of the line charge, and hence charges are flowing in that left-right direction. Your electric field will also be in the left-right direction. Hence E can be drawn along the direction of the charges. Now I am taking a point on the Gaussian surface. If I am taking a point on the Gaussian surface, then across the curved surface the dA will be drawn perpendicular. So if you are drawing dA perpendicular, this will be how it appears to be. Okay, so now from this figure it is clear the angle between E and dA will be equal to 0. Here charge placed on both sides of the line, hence there will be no electric field on top and bottom surface of the cylinder. Electric field is towards a curved surface. Now I am going to the Gaussian expression. Q by epsilon 0 is equal to integral E dA. E dot dA, that is equal to E dA cos theta. Theta is equal to 0, so I will get integral E dA. And now here we are using a line charge, hence that line charge will be having a line charge density which is usually represented as rho RL equal to Q by L, charge per length. From that I can write Q is equal to L into rho L, that I am substituting in this equation. So rho of L into L by epsilon is equal to integral E dA. E is a constant because the Gaussian surface is uniform, so E into integral dA, and since it is a cylinder, the area is equal to 2 pi RL, where R is the distance of the point P from Z axis, and you are substituting this expression here. So L into rho L by epsilon 0 is equal to E into 2 pi RL. Rearrange the equation, you will get E is equal to rho L by epsilon 0 2 pi RL. From that you know D is equal to epsilon 0 E. So substituting in that equation, you will get D is equal to rho L by 2 pi R unit vector OA rho. So that is the final expression for a line charge.